Hi all! There's two parts to this one. One is working through another messy definition of the derivative, and two is continuing to practice interpreting the meaning of functions and derivatives. So I think this is a great one if you're feeling comfortable for you to try on your own and then use the video to check yourself. But I'll go ahead and power on through, so if you need it, you can watch and see what's going on. The first part of this problem is more of a pre-calc problem. We just want to find the value of the function when r equals 2000 and talk about what that means in the context of this problem. So this could really just be a technology question, and I went and did that work. When I plugged in 2000, I got 800.005 as my answer. And we just want to sort through the meaning of this. So if we read through the question, we have a company manufacturing rope, and our function is supposed to give us the total cost of producing the rope when we make r feet of a rope. So the 2000 is feet, and the 800.005 is dollars. I don't know why that turned into an 8. There we go. So I would say explain using everyday language would be something like, when the company produces 2,000 feet of rope, their total cost is $800.01 is probably a reasonable place to actually round that one. So make sure when you're doing that you're using both of the numerical values in your answer. You're using units on both of those numerical values, and the everyday language part means I don't need you to really get into the mathematical wording and the calculations you did. Just what does this mean if someone asked you to solve this problem for them. Okay, part B gets back into a calculus question. We are now asked to find c prime of 2000 and explain its meaning. So not the value of the function, but the value of the derivative. What does it mean? To find the value of the derivative, c prime, we will need to set up our limit definition. So the limit as h approaches 0 of c of 2000 plus h minus c of 2000 divided by h. And this is going to get pretty messy with the function that we have. So let's see if I can fit it in here. The limit as h approaches 0. Okay, so our function, if we want to plug in 2000 plus h, we're going to have to square it and multiply by 0.35. We're going to have to multiply by 100. We're going to have to add those up and add 10. And we're going to have to divide by our 2000 plus h. So I'll write that all out. This is just the first piece, and it's kind of a messy one. 0.35 times 2000 plus h squared plus 100 times 2000 plus h plus 10 all over 2000 plus h. Okay, and this is kind of cramped, but note that we already did this calculation, c of 2000. That was what part 8 asked about. So we actually already know that we're subtracting 800.005. And for the difference quotient, I would not use a rounded value there. I think we might miss some cancellation or some nice things if we start rounding numbers when we're doing difference quotients. Okay, so there's my setup, pretty messy. Let's go ahead and start trying to simplify. While that is fairly ugly, the nice thing is that in terms of fractions within fractions, there's just one. There's just the 2000 plus h. So let's start by clearing that out. This isn't quite going to fit, but we would multiply top and bottom by 2000 plus h. And we would end up with, in this first fraction, when we distribute that 2000 plus h, that denominator cancels. So we'll have the limit as h approaches 0 of just the numerator left over. 0.35 times 2000 plus h squared. I'm going to go ahead and start. No, we'll go ahead and we'll just write it out. I was going to start doing a little simplify, but one write out might be good for us so we don't lose track of anything. Plus 10 minus 800.005. This one, when we multiply by 2000 plus h, nothing cancels, so we'll actually have to do that multiplication. In the denominator, I now have h times 2000 plus h, and I'm not going to distribute that through because my whole goal is to cancel that h out of the bottom, which means I want it factored. Okay, so limit h approaches 0. Keep writing this until you actually let h approach 0. I can tell right now that if I did let h go to 0, I would still have 0 in the denominator, so that would be no good. On the top, I need to multiply 2,000 plus h by itself. So 2,000 plus h times 2,000 plus h, and that will give me 4 million. That's 2,000 times 2,000. And then a 2,000h plus 2,000h, which will be a 4,000h, and an h squared. So make sure you FOIL that out. You can't just distribute powers. You have to multiply 2,000 plus h by itself. In that second chunk, I can go ahead and distribute the 100 through now. So I'm getting 2,000 and then 2 more zeros. So 200,000 and 100h. Oh, I'm going to run out of room. Plus 10 minus, okay, we need to multiply the 800.005 times the 2,000. And when I check that, I got 1,600,010. And then last little bit, we need minus 800.005h. Okay, so I kind of had to run onto 2 lines there, but that's all over h times 2,000 plus h. Okay, one more big rewrite, but I can start to maybe do a little bit of combining. I need to distribute the 0.35 through. So I will get limit as h approaches 0. 0.35 times 4 million is 1,400,000. And then 0.35 times 4,000h is 1,400h. And then we'll have a 0.35h squared. Okay, let's see if we can do just a little combining here. I have a 200,000 minus 1,600,010. Oh, and also a plus 10. So actually, that's just going to knock out this minus 10 right here. When we combine those two, that'll become a 0. Okay, so 200,000 minus 1,600,000 should be a negative 1,400,000. I like seeing that. That's actually quite promising. And then if we combine 100h minus 800.005h, we get negative 700.005h. It's improving a little bit. All over h times 2,000 plus h. We're very close. I'm going to just run out of room. I get to cross out the 1,400,000s. I can combine some h's. So we still haven't taken the limit because we still haven't canceled that lonely h out of the bottom. That has to go away first. Now we need 1,400h minus 700.005h. which should put us just shy of 700. So what is it? 699.995, shy of 700. And then we still have the plus 0.35h squared all over h times 2,000 plus h. And since I've scrunched myself for room a little bit, I'm going to go ahead and do this factoring right up above. So we need to factor an h out. And that leaves us with 699.995 plus 0.35h. And that allows us to cancel the h out. So finally, we're to the point where we can let h go to 0. And when that happens, let's see, I'll use that blue actually. This term goes away, the 0.35h, and this h doesn't really have any meaning on the bottom. So we end up with 699.995 divided by 2,000, which is roughly 0.35. I rounded just a little bit there. So finally, kind of a long one, but we got through, we got to the answer. The derivative, what was this? C prime of r. Nope, we can be even more specific. although I might not have room, C prime of 2,000. So the derivative when R equals 2,000 is 0.35. And we want to think about what that means, and then that will help us answer the very last part of this. That's saying that when the company is at a production level of 2,000 feet of rope, the cost, the total production cost, is increasing by 35 cents per additional foot of rope. So remember, this is giving us slope. We're inputting feet of rope, we're outputting cost. So our slope is going to be change in cost over change in rope, which means that 0.35 is dollars and that 1 is feet. So total cost is increasing by 35 cents per foot at the 2,000 feet of rope mark of production. This does not mean that it's always 35 cents per foot. This absolutely is changing depending on what production level we're at, but that's what it means for us right now. Based on that interpretation, and let me say before I move on, again, it's really important that you include all numerical values in your interpretation, your explanation. So the 2,000 should show up, the 0.35 should show up, and the 1 should show up. Even though I had to write that in for myself, you need to know that slope is a ratio. So if it doesn't have a fraction already, you have to put an over 1. You also need to include the units on all of those values. So the fact that the 2,000 is feet, that the 35 cents is dollars, and that the 1 is feet. All of those things are important. Okay, last part. Based on that explanation that we just talked through, could we estimate C of 2,100? So the cost at the production level of 2,100 feet of rope. And I would say yes. What we're supposed to be looking back at was that when we were manufacturing 2,000 feet, we got a cost of $800 and roughly 1 cent, half of a cent, I guess we would say. What we've just decided is that if we want to produce an additional 100 feet of rope, it's going to cost us 35 cents per foot. Well, I guess it's dollars, not cents, even though I said it that way, which means that the 100 feet, when we multiply, will cost us $35. So our grand total should be $835, and half a cent, we're going to round that up to 0.1 or to 1 cent, 0.01. So roughly $835.01. That is an estimation using the tangent line. You can actually find C of 2,100, see how well we did if you want to, but that is something we do with tangent lines. Use them to give us much quicker, easier estimates of values of functions that are a little messy to make calculations with. All right, that's all I've got for this one. Thanks for watching.